Hello everyone, my name is Yi Tian from Institute of Robotics and Industry Informatics. Today I'm going to introduce our paper, Event Transformer FlowNet for Optical Flow Estimation. Event camera can detect fast motion with low latency, high dynamic range, and low power consumption. In this work, we address their use for fast and robust computation of optical flow. We present ET-FlowNet, a hybrid RNN-VIT architecture for optical flow estimation. We perform end-to-end training with self-supervised learning method. Our results show comparable and in some cases exceeding performance with the state-of-the-art event-based optical flow estimation methods. The model of visual transformers has gained popularity as an ideal candidate for the learning of global context in visual tasks, and we argue that during rigid body motion, these long-range dependencies in the image can also benefit motion estimation. We follow a similar U-Net encoder-decoder architecture and use convolutional GRU unit to extract the temporal information and incorporate a token pyramid aggregation TPA transformer block connecting the encoder and decoder, inspired by the use of transformers for video reconstruction. The TPA module connects to all the feature map outputs from encoders. The transformer encoders model the internal spatial dependency of each feature map, while the transformer decoders capture the interactions among all the feature maps of different scales. In such a way, we fully model the interactions across time, space, and scale. For learning, due to lack of label training data, optical flow is often learned in a self-supervised manner. In our work, we train the network using self-supervised learning with contrast maximization loss. The method aims to find the optimized parameters that compensate for the motion and provide a deblurred image of warped events upon convergence. We first generate the per pixel and per polarity average timestamp of the IWE via bilinear interpolation. The contrast maximization loss is expressed as the scaled sum of the squared temporal image both in the forward and backward directions. In addition, we add a smoothen in the neighborhood pixels as regularizer as common practice. We train our model on FPV dataset, following the same pipeline as in ConvGRU, EV-FlowNet, and FireNet. Thus, these two networks are our main target for evaluation comparison. In general, our method outperforms FireNet in all sequences and beats ConvGRU, EV-FlowNet, especially with a large margin for the on-dot day 1 sequence, and yields similar results in the in-dot sequences. The qualitative results from NV6 dataset further confirms that. The first column is the event input with green and red color indicating polarities. The second column shows the dense ground truth data, while the rest column shows qualitative results tested on different models. The results have been masked where there are presence of events. As we can see, our results show more consistency compared to the ground truth data, especially for these sparse and far-away objects thanks to the transformer block that capture better the spatial dependency. Further, we perform ablation studies based on 3 factors. The first, with or without the transformer block. The second, the number of encoders and decoders included in the transformer block. And the last, their stacking structure. Our model ET-FlowNet 4T beats the baseline models in most of the sequences for DT1 case and in all the sequences for DT4 case. In conclusion, in this paper, we propose the ET-FlowNet, the first framework for event-based optical flow estimation using transformer. Our network combines transformer with RNN to fully model the interactions across time, space, and scales, and achieve comparable results and superior in some sequences compared to other self-supervised methods. For the future work, we aim to simplify the complexity of the network for less memory consumption and expand the self-attention mechanism for the temporal domain. That's all. Thank you very much.